a lot of people forget that all the modules you can buy, they all look the same from the outside. But it's really how do you do the interconnection in order also to have the reliability for 15 or 25 years. I think there was the blackout in Spain. Yeah. So while the cause is not fully understood, I think, I would argue that having more sources that create grid stability could have mitigated also this impact.
This is the podcast for Ingénieurs, the podcast you just have to listen to if you're interested in what's going on in the semiconductor market. My name is Kelsey Markle and I'm your host. I'm joined by Marco Werr, who is our Global Application Manager for Utility and Commercial Energy Storage Systems. Marco, thank you so much for being here.
Yeah, thanks for having me here.
And this isn't your first time on the show. We also talked about ESS in the past, right?
Yeah.
Yeah, today we wanted to look more about how this shift from renewables to renewables is affecting ESS and how ESS can possibly provide solutions to this unstable grid situation. So let's jump right in. What does the market look like right now?
Yeah, so let's talk about the market and also there's a trending topic, grid forming. And if you check now all the data sheets and also if you go to trade shows on the energy storage, you all see this grid forming label. But it's not really defined what is behind it. And what I can say is that there's a global shift from fossil energy that we all know. So we move away from coal, gas, and also nuclear power. And this is also accelerating the adoption of renewables. And based on IEA, there's probably a threefold increase in the next 10 years for the renewables. And on the other side, to cope with that, we'll see let's say a fivefold increase in the batteries or the, let's say, storage capacity. And most of this will be lithium-ion batteries. And so it's all about grid stability here. So in the end, you have synchronous generators from the fossil fuels. And those, they get changed to inverter-based resources. And so just an inverter is probably not able to cope with the grid stability or provide the grid stability that rotating mass could have generated.
Okay, yeah, we've actually seen this in the news even recently, some certain events happening in Europe or around the world with grid instability, right?
Yes, so I think there was the blackout in Spain. Yeah. So while the cause is not fully understood, I think, I would argue that having more, let's say, sources that create grid stability could have mitigated also this impact. Mm-hmm. And we have to really look out in the future to have these sources available, and the systems need to be designed like that to really step in when there's grid instability that is caused by the renewable energy. So this is the cost of the changing to the renewables also.
Yeah, everything comes with a cost, I guess. Great for the planet, but we have to deal with it somehow. I remember last time we talked about front of the meter versus behind the meter, right?
Right, yeah.
Can you tell me, just remind our listeners, what is the difference there?
So front of the meter installations, they're usually on the, let's say, utility grid side. So connected directly to the grid, and they focus on grid services, let's say also supporting the grid stability. And then we have behind the meter, which are usually installed at customer premises, meaning that if you have an industry or if you have a home, then it's usually after the meter. And they're a bit different use cases. So on the behind the meter system, usually focus on self-optimization. But for commercial systems, we also see the use of some ancillary services for grid stability, but this is really, let's say, not a standard case. And then for the front of the meter, it's really about participating in the wholesale market in the end and providing different services such as capacity, energy, or ancillary services to stabilize the grid or cope with this fluctuating energy prices the renewables generate.
Okay, let's talk a little bit about how technology is evolving then, because we're moving from fossil fuels to renewables, and that puts some different kinds of pressure on the grid and different kinds of pressure on our energy storage systems. This evolution in energy source, how is that reflected in the technology evolution?
Yeah, so in the end, you have to look at the energy storage, and as I said, most of the new installations will be battery energy storage systems, and so there's an inverter that then has to inject or store energy based on the grid stability, and in order to cope with that and let's say to make money out of this, there are multiple revenue streams you could work on, and often a lot of them are stacked to generate also a high return of invest in the end of this energy storage system.
Okay, so it's not just the technology that is evolving, it's also the business use cases that are evolving.
And it's very complex, I'd say. So there's so many different use cases. But in the end, we as a semiconductor supplier, we have to look at, let's say, the limiting factors. And I don't want to get too much in detail in that because this is quite technical, and I guess we also have a follow-up on that one.
We have a follow-up episode,
Yeah. But so the basic, let's say, business models in the energy storage is, let's say, energy arbitrage. So you buy energy when it's cheap, and then you sell it again to make money out of this. And then you have capacity service. So this is just providing availability of capacity during peak demand. So maybe there is not even an event, but you still have to provide this availability. And this also means your system needs to be available. This means also the subcomponents need to be reliable also at some point.
This just means having energy ready to go when we need it.
Yeah.
Okay.
And then you have this ancillary services like fast response in case there's some instability in the grid. Yeah. Mm-hmm. And then, of course, you stack these services.
Okay. So what does this mean then in terms of semiconductors? We're a semiconductor company.
Yeah.
What are all these different use cases? What demands do they have on the semiconductor components?
Yeah. So you have the standard grid following inverters. Most of the systems are doing this. And here I'd say there's also some demands on the semiconductors, especially because you want to increase the power density of your system. Mm-hmm. And also, why do you want to increase the power density? So you have usually a 20 feet container, and you want to put as much as batteries in there as possible to make most out of the used space as a return of invest. And how can we support this? I mean, you could increase the power density of a module by changing the technology, for example, in the module. Mm-hmm. And then you could also increase the power density by using a different technology in the modules. So, for example, silicon carbide, mm-hmm. because here you can then reduce the system cost and also the system size, the weight of the system, and also gain some space or volume then for more batteries, and also increase the efficiency and reduce the cooling demands, mm-hmm. and so the overall efficiency of the system can also increase.
Okay, so on the material side, is there anything like within the package, anything else besides just changing the materials?
I mean, the basic material is a chip, right? Yeah. But then a lot of people forget that all the modules you can buy, they all look the same from the outside. But it's really how do you do the interconnection in order also to have the reliability for 15 or 25 years. And here we come to the topic of grid forming, where you add a lot of stress on the device. So you have to overload the devices. You might have some different circles or thermal circles that then reduce the lifetime of the devices. And here we, Infineon, as an innovation leader, we try to let's say have solutions to cope with that. So to not have to, let's say, change the complete system to or really over design the system to work, but to have the a module that the customer knows, but in an advanced version. Yeah. And here, for example, we have .xt technology. So .xt stands for extended lifetime. Mm-hmm. But you could also use it in a different way. So you can have the same lifetime and then increase the current. So you have a higher power density. Yeah. Mm-hmm. So it really depends on the design needs of the customer. And these are
.xt, you said extended lifetime, but it's the interconnection technology,
right?
Yeah,
it's an interconnection technology, but it leads to extended lifetime at some point, yeah.
Okay.
So when we look at this grid forming, it's all about the overload and power cycling. And here, I'd say if we look in the portfolio, we have recently added an XHP device. So this is a new package, but it's a standardized package, especially for silicon carbide. So high voltage silicon carbide, so 2.3 kV or 3.3 kV. So if you want to go higher with your DC link voltage, so above 1500 volt, this can have some system cost savings. You can already do this with our XHP in a simple topology. It's just a 2-level topology. And if we look more in, let's say, in the standard systems, and the 62 millimeter, for example, is a very proven package in the market, we also have some innovations in this. So here we introduced recently 2 versions. One where we increased the diode current by 20%, and one where we increased the IGBT current by 20%. And the one with the increased IGBT current is to increase the power density of a solar inverter, so unidirectional use case. Mm-hmm. And the one with the increased diode is then for more bidirectional use cases like in energy storage. And here, just changing to this new module, which also comes with an increased junction temperature, so that helps with this, let's say, overload conditions, you can increase the power density of your system by 13% in a standard topology. Yeah.
Okay. So you're touching on a topic that I think I'll do a deep dive on later with Manuel, our colleague, because we're really going to talk about grid forming versus grid following and what that really means for the different requirements from an unstable grid and how we can cope with that. But great. Thank you so much, Marco, for giving us a preview into the topic. Yeah. And it was great having you. And for our listeners out there, be sure to stay tuned for part 2 of this episode on ESS, where we're going to talk about grid forming versus grid following and how semiconductors can make a difference in coping with the unstable grid. Thanks a lot.